In this video, we want briefly to compare cache coherence and memory consistency, and then talk a little bit about the assumptions that underlie sequential consistency. Recall that cache coherence deals with ordering writes to a single memory location. It doesn't have anything to do with writes to different locations, and it's not needed if there is only one copy of the data. So if there's only a main memory and no caches, you don't need to worry about cache coherence because all changes are made to the single copy of memory and they must be made in order as seen from anywhere in the system. But if you have multiple copies, as in caches, then you need to make sure that the changes made to one cache are seen in order by the rest of the system. Memory consistency, on the other hand, deals with ordering of reads and writes to all memory locations. And even if you didn't have a cache, you'd still need it. See, with cache coherence, you're dealing with writes to a single location, and there's only a single location if you don't have a cache. But with memory consistency, you've got multiple locations, even if there isn't multiple copies of a particular data item, and accesses to those locations need to be kept in order. Now, why is a memory consistency model needed? We need it so that what goes on in memory is consistent with what the programmer expects. Here's an example with a couple of processes, P0 and P1. P1 sets datum to a particular value and then notifies the other process that it's ready by setting a value in a shared location. The other process is waiting for that value to become ready, and once it's ready, then it assigns it to something else. Programmers expect then that the value that's assigned in P0, which is 5, is also the value that's assigned in P1. But this expectation can be violated in two ways. First of all, if S2 appears to be executed before S1, in other words, if the datum is ready seems to happen before the value of the datum changes, or if S4 appears to be executed before S3. So if we assign the value before we wait for the datum to be ready, both of those violate the expectation of program order. So hypothesis 1 then, for sequentially consistent memory, is the program order expectation. Programmers expect memory accesses in a thread to be executed in the same order that they appear in the source code. And now, since we have different threads, different processors, we need to stipulate that all threads, and not just the executing thread or the thread that we're concerned with, are expected to see memory accesses in the same order. So we can't have, our processor see access 1 before access 2 and some other processor see access 2 before access 1. That's illustrated by this 3-process example that you see on the screen there. P0 sets x equal to 5, and then it sets x ready to 1, signifying that the value of x is ready. And then P1 loops while x is not ready, and when x does become ready, then it sets y equal to x plus 4. And then it sets xy ready to 1 to signal that both x and y are ready. P2 is waiting for both x and y to be ready, and when it finds that they are, it sets z equal to x times y. Now let's say everything is set to 0 in the beginning. As a programmer, what would you expect to be the value of z at statement S7? And I'm going to make that our first quiz of the day. So I'm going to ask you that, and then I'm going to ask you to finish the following statement. It implies that if the new value of x has been propagated to P2, that new value of x has also been propagated where else? Now, as a way of formalizing what we just said, we'll call it the atomicity expectation. That is, if a value appears to be changed, the value in a memory location appears to be changed at one place, it also should appear to be changed everywhere else in the system, or as the statement says there, with respect to all other processors. How can the atomicity expectation be violated? Well, here's one way. If new values of x and x ready have been propagated to P1, so they've reached P1, but they haven't reached P2, so something else can happen before they reach P2, and then that's going to violate the atomicity expectation. What is it? Well, step 2, new values of y and xy ready have also been propagated to P2 before x finally makes it to P2. And if that's the case, what's going to happen? What value are we going to have calculated for z? Well, when x is propagated to P2, P2 has already read the old value of x, the old value of x being 0, So it's set z equal to x times y, and that means that z has been set to 0 instead of what it should have equaled, which you told me about in the quiz just a minute ago. Now remember that I said that this is one way that a violation of store atomicity can lead to a wrong value for z, but there's another way that an incorrect value could be written for z as well if things happen in the wrong order. So what I'd like you to do is tell me what other incorrect value could be written in that case. Okay, so in that situation, a new value would have been calculated for y before the change in x had been propagated to P1. Let's summarize what a programmer expects then. Memory accesses that come from a single processor should be performed in program order, and each of them should be performed atomically, which means that they're seen throughout the system. And that's basically what Lamport defined to be sequential consistency back in 1979. A multiprocessor is sequentially consistent if the result of any execution is the same as if the operations of all the processors were executed in some sequential order and the operations of each individual processor occur in the sequence specified by its program. So where we had the little needle that went around to point from one processor to another, you remember about 4 lectures ago? That's exactly the definition that we were going through at that time, and that's what programmers expect to occur. So sequential consistency does a very good job of obeying programmers' expectations.